Hello again, and yes, welcome to this video lecture where we present the solution or approximate solution actually to the Muad'Dib's jihad problem 7.4. And so far I've given this explained these solutions that are M files since we use Octave by using Octave. So now I hope that using the Octave is you are more or less fluent in that. So I will just go through this code and the new parts or the new point through these lecture notes and not opening Octave. Of course, here is the link where you can download this M file. It's called jihad.m. And yeah, the beginning is the same as as always. So it's telling something what's happening here. So this is Muad'Dib's jihad problem 7.1 from linear programming with SPICE. And then there's a data of the problem, so it's a C, A, and B. And I think these are, I think this should be relatively clear now what happens. Again, I've written maybe slightly different way, so I'm putting the opening bracket here on this separate line and closing bracket here in a separate line. That's just matter of taste or style. Also, I've given these, I'm not using transpose, instead I'm using these semicolons here, so this will automatically be a column vector, and then these comments here are kind of natural. So this means the influence of Fedaykin, Conscript, and Sardaukar. And then resentment tolerances, these are the B's for Arrakis, Kaladan, Chapter House, Giedi Prime, X, Kaitain, and Tleilax. And then here is the tolerance matrix, same way as opening bracket and closing bracket are here on the separate lines. Note that I have used a big spacing here, so it's more obvious and easy to see what are the numbers. And here are, of course, the planets again. And then I've used here a comment line also, so to explain that these are the Fedaykin resentments, Conscript resentments, and Sardaukar resentments. Okay, a slightly new thing happens here. So there are two new things here. This is not related to this sensitivity. This is related to the fact that I previously said that it's a good thing to have the data section, so that if you just change the data, everything else works just fine. And it was not completely so in the previous cases. So in the previous M files, if I change the dimensions of the data, the rest would not work automatically. So for example, if here I increase, if I have further different kind of troops, or I remove some troops, or if I add planets or remove planets, then I want this M file to work in any case. So all the changes that I need to do are in C, B, and A, and everything else would work just fine. And this is the trick what happens here. So what can change then? This C type, constraint type, can change in the sense that the length of the string is different. It's always U, upper bounds. The tolerance levels for the resentment are upper bounds. So I need to have U's, that's fixed, but there are different number of them. And the number of U's is the number of planets which could be recovered from the length of B, for example. So this is the kind of, maybe this is not so elegant, but at least this works. So how do I build this string? I start C type is an empty string. So it's a string with just quotes and nothing inside. Then I go in a for loop. So I goes from 1 to length B. So this for loop will be looping as many times as we have planets. And then the C type will be given, and this is a kind of funny construct, but it turns out that this works. I set in brackets, so it's a C type, whatever it was before, and then in the quotation U, and then brackets closed. So this will each time the loop is run, will put another U in the end. Okay, maybe I'll show you. I said that I will not use Octave here, but let me make myself a liar and show you a little bit how this works so you can see it. So I start with C type is empty. Now I don't put semicolons there so you can see the output. Okay, now C type is nothing. Then I say C type will be C type, and then, well, let's put the U there. It could be any. Now it's like this. Then I do it again. Then I do it again. So I think it's obvious how this works. Let's do something else. Let's put L, for example. Then it's an L. Okay. So this does precisely what we want to do. And for the variable type, so almost always our variables are continuous. So this will work the same time, similarly, or in the same way as for C type, but now for variable type, which I called V type, and then the length is of course the length of C, the objective function. Okay, that was a kind of maybe unnecessary trick, but now we are in the nice case where the solution with GLPK will work completely. If I change C, A, and B in the data section, this will change accordingly and everything works just fine. I don't have to here make sure that these are correct. They will be correct because of we just set them to be correct. So this we have seen. It's a formally product mix problem, although a funny one because the products we are going to mix is the legions into a rapid deployment force. But what is new here? New is that now I'm asking for, well, basically full output. This E I don't actually care. It's there just because I have to give it because the fourth argument is the one, fourth output variable is the one that I'm interested in. So I have to give the E to somewhere, or the third one to somewhere. So I don't care about it, but for the technical reasons I have to call it like this. And now this extra, that's the key thing here. GLPK in this fourth output argument, which we call now here extra with teenage spelling, this will contain many additional information. In particular, it will contain the shadow prices. And the shadow prices are in the extra field lambda. And since I don't want to write this long, so this is in some sense this is just a shorthand notation, so I will make a new variable lambda that will take the vector extra dot lambda. Okay, this is just to write things shortly. So here I will have the shadow prices for this problem. And yeah, basically we are finished there. There we have all the information we need for this problem, but let's make an output that is a bit more informative and also slightly compact. So now I take a variable called optimal legions, will be X, so that's the optimal solution. It will give me information how many different legions I have the rapid deployment force. I make it a row vector, so the point is that then I can actually don't have to scroll the output because column vectors will take too many lines. The same for optimal influence, so this will be the Z. Again, I transpose it so that it's a shorter the output. And then marginal influence gains. So this will be this shadow prices lambda. Same thing, I transpose it. And this also somehow explains why the shadow prices are called marginal prices also. So it gives the marginal influence, so influence the margin. So if I increase some constraint or the upper bound, which is the tolerance levels for the resentment, how much the influence on this margin will increase. And these are the lambdas, these are the shadow prices. And finally, a new thing here, free tolerances. So this was the upper bounds, and this has to be bigger than or equal to a times x. So this difference here will tell how much of this resentment tolerance is not unused in this rapid deployment force that we are building. Just to see how much remaining tolerance there is, so to say. And you notice that there are semicolons missing there, so this means that the values of these will be printed. And indeed, this is what happens. So of course you should download this jihad.m yourself and check in Octave that you get it working. This is the output what you should have. So optimal legions will be 370 Fedaykin legions in the rapid deployment force. No conscripts at all. Okay, maybe a bit surprising, but that's how it is. And 225 Sardaukar legions. The optimal influence will be 5275, whatever influence unit is. And then there are marginal influence gains. So 1.5007. And these are related to the planets, of course. And then there are free tolerances. So this means that in the last planet, and let's see what was the last planet, that was Tleilax. There is no remaining tolerance at all. So if we send the rapid deployment force to Tleilax, it is kind of no more tolerance left, so it's maybe on the brink of rebelling, but it's not yet rebelling. The same thing for this. So this was 1, 2, 3. So it's the fourth planet. Let's see what's the fourth planet is. This is Giedi Prime. The same thing there. Giedi Prime is the Harkonnen planet, if I remember correctly. Alright, so those planets, the influence is tolerance is completely used. There are no more tolerances left. The rest of the planets, there are tolerances left. Okay. Now, that was actually not what we are interested in, but it's informative to look at that, because let's now look what we are interested in. The marginal influence gains. So this tells how the optimal changes if we get 10, actually 1 unit here. This is what it tells here. So these three first planets, it's 0 marginal gain. And well, this is obvious from this one here, because there are tolerances left. So if we get a little bit more tolerance to resentment there, it doesn't help us at all, because we are not we are not using them at all. So whether this 9 is increased to 10 or whatever, there's still something left. So there is no gain here. These are zeros. In the same way, these two corresponding to these two zeros, there is some tolerances left. So if we get something more of something that we haven't used completely, then getting something that we are not using is useless to us in a sense. So only these two zeros, so the Tleilax and Giedi Prime, if I remember correctly, these give us something on the margin, because we are exploiting all the goodwill or resentment tolerance. And here, this is the partial derivative 1.5 here and 7.0 here. So this is bigger than this. It means that on the margin, this gives 7 influence units per 1 tolerance level. So the answer is that we should give it to what? The last planet, that was here, that was Tleilax. So we should make the planet Tleilax bestow it the special imperial status, and in this, to be exact, then assuming that this change of 10 units is small, it's not clear, we get 7 times 10, so 10 units small influence for our force. Okay, so now we have an answer to the question, which may be correct, maybe not. Because it's unclear whether this change is small, but nevertheless, it kind of tells us that this is the all the other planets. It's not so critical for them. It's not too critical for them what is the composition of our rapid deployment force. But for this planet, Geary Prime, let me check that it really was Geary Prime. Yes, it was. And for planet Tleilax, they are critical. I mean, they are on the brink of rebelling, and if we increase their tolerances, then this will give a little bit more influence, so we can increase the influence of forces a little bit, and if we give the special imperial status to that last planet Tleilax, then it will increase much more the influence of our rapid deployment force. Okay, so that was the story and the solution. So we have a couple of exercises for this. So the first one is, and this is important to do, is to solve this special imperial bestowing selection problem. So this Muad'Dib's jihad problem 7.1 in the safe way. So really looking all the 7 different LPs 7.3 as it was explained in the remark 7.2. So this is the exercise safe jihad policy. And yes, make the comparison to see whether it is the same solution as it is in this differential form. Then another exercise in this section 7.6, Tleilax rebellion. So let's make things even more convoluted. So suppose that before this rapid deployment force was constructed, so before we collected all these legions, during this or somewhere before the decision of how to build this force, planet Tleilax decided to rebel against the just and holy rule of Emperor Paul Muad'Dib. I mean, for some reason they just decided to do that. And of course, when a planet rebels, what is the solution? Well, you send a permanent garrison there, or troops, of course. So it doesn't make any sense to send this rapid deployment force there, because now they show that they are rebelling, so we will have a permanent garrison there so far. So this rapid deployment force is used only on the other planets now. Planet Tleilax is kind of scrapped from the consideration. There's a permanent garrison there, and let's assume that everything else stays the same. This is always what we assume in sensitivity analysis. So other planets don't. Let's hope that there is no snowball effect here, or if there is, we omit it in this consideration. So now we only have the other planets except Tleilax, and the question is the same. To which planet should we grant the special imperial status? And maybe I will say a small point here. Now you might think that okay, this last one is out of the question, so obviously the next one that gives us the on the margin most influence is this 1.5, that is Giedi prime, and you might think that then you set it there, and yeah, is it so? Is it this simple? All right, more exercises. So exercise 7.7, and now let's go back to more peaceful exercise. So let's have this Muad'Dib bakery nutrient purchase problem. So we have this Muad'Dib bakery problem 5.1, same as 4.1. We have considered this problem a lot. So why not consider sensitivity analysis and shadow prices in that problem also? So the Muad'Dib had these nutrient powders. So the sensitivity shadow prices are related to these constraints. In this case, the constraints were the available nutrient powders. So let's assume that Muad'Dib bakery has the opportunity to buy nutrient powders from the notorious seeds Chakurutu. So there is a merchant from Chakurutu tells Muad'Dib bakery that okay, we have nutrient powders to sell, and now we have to discuss the price. Yes, I mean, very natural problem. No, so how much should Muad'Dib bakery be willing to pay for these different nutrient powders? A simple, obvious problem. Solve this. And again, the safe way of solving it would be a very complicated actually now, but at least look at if there is just small amount of nutrient powders for sale, then maybe the shadow prices give you the answer. Okay. So it's 22 minutes now in this video, but there is not much left in these shadow prices, so let me put it in the end of this video. So let's not have a new video for this last remark. Yes, so this is unfortunately some of the notation is relatively small, so I make this font now bigger and correspondingly my face smaller, but I suppose you have had enough on my face already, so maybe this is just good. Let's see if this now works well. Okay, maybe I can have it. All right, so this is remark 7.8. So this is something I should where I collect some remarks on shadow prices and what and why. It's kind of what these are and why we are interested in them. So the shadow prices are the partial derivative, how the optimal solution, I mean the objective, changes when the resource Bj changes. And these are also denoted by lambda j. This is the notation I will use here. And sometimes there are pi j's or mu j's also. So then a remark of these different names. So the shadow prices are called shadow prices. Why? Because they are actually the optimal solution. They are the optimal decision for a shadow problem. So there is a shadow problem that somehow shadows the problem we have. So what is this shadow problem? It's actually also called a dual problem, and we have actually seen a dual problem already, but we will consider them more systematically later. And this is basically the reason also why these shadow prices are called dual variables. So whether you consider shadow problem or a dual problem, then you call them shadow prices or dual variables. Maybe dual prices also could be used. Okay, if you think about this from the duality perspective, as we will do later, then this makes a lot of sense. At this point, it maybe doesn't make so much sense. At this point, the name marginal prices for shadow prices makes more sense, and I think this would be probably the most natural way of calling them. Unfortunately, usually the shadow prices is the most common name, so that's why I used it. If I could decide what is the names people use all around the world, then I would say that you should use marginal prices. This kind of is, I think, most obvious. So what does it mean that they are marginal prices? It means that the price of the resources you have, so the B's, the tolerance levels, the amount of nutrients, what is their value price for you in the margin? So in the margin, meaning that if I get a small increase in some resource, how will it increase my optimal solution? So it will increase it by lambda j. So if I get 1 unit of bj more, and assuming that this change means it is a small change in this context, then I get lambda j units increase in my optimal solution. So I think this one here, the marginal price interpretation, is, at least for me, this is the most natural one. This is the way I think shadow prices. Okay, and that's maybe the most important thing to understand here. So let's see if I can paint this for a while. So this one here is the one that you need to. So if you understand this, then you understand what the shadow prices are, and if not, then not. Okay. So then comes something. So let's get back to this formalism with partial derivatives, and now we have even more complicated formalism because we add calculus and linear algebra together, which is something that could be called multivariate calculus, I suppose. So if you had a course like that, then I hope this helps you. This puts things into that context. If not, there is a risk that I'm confusing you. So let's see. So the idea is that suppose now there is a z star. This function is actually linear for small changes. So this is what's important here from the actually theoretical point of view. I mean, we have a linear problem. The LP is a linear problem. Everything there is, I mean, the objective function is linear, the constraints are linear. But that doesn't mean that the solution of LP is actually a linear in its data, constraints, and objectives and so on. But it is actually if the changes are very small. So this means that actually in the approximate differential there is no approximation, it's actually equality. So what does it mean? It means that if I look at I have this optimal at C, A, B, and delta. Now I'm doing this a bit more complicated. So now the delta is the small changes in every direction. So the resource vector, resources change some delta. Well, delta is, I suppose, small. And then I want to calculate what is the optimal nu when the B is changed by this delta. It is exactly the original one plus then these partial derivatives in a product with this delta. This is just a linear algebra combined with multivariate calculus. And then here I'm just denoting this by the lambda prime. Okay, a little bit of funny notation. What does it mean that I have a partial derivative when there is a vector here? Well, that's actually the gradient. So gradient is the vector where you have collected all the partial derivatives. So it can be written this way, which is unfortunately now that this becomes a very, very tiny script. Okay, so this point, if you remember your multivariate calculus and linear algebra, this should be something that helps you to understand it. If not, then you might be confused. What what you should remember here is 7.9 in the sense that this here equals this. So this is how the lambdas, the shadow prices come. If this delta vector is small enough. Okay, that's the why and what of shadow prices. So the idea is really here that if the parameters here be changed, what happens? We can of course calculate everything, and then we get a lot of numbers, and maybe we can figure out and get an impression or visualization what's going on. I wouldn't. Maybe you can. But for this, it's kind of more clear that okay, the change is I have the original, and then yeah, this is the increase of this delta to this, and this gives how much each delta component gives me more influence or optimal z star, I mean optimal value. Okay, then a final point here. This is what we actually had. I explained about how these zeros correspond to these non-zeros and vice versa. So there is some kind of complementary zeros there. So the final point that is that if I have a shadow price 0, this usually, I mean it's not exactly always, but usually it means that not all the resources Bj are used in the optimal solution. So it means that if I look, so this is for j, this is the constraint there is, I put there the optimal solution, there was the upper bound Bj, now it's strictly less, so it's not completely reached, so there is some slack there. So this is sometimes related to what is called complementary slackness. So, and this of course makes sense. I mean it's not completely true, but it's kind of, what should I say, true enough that if you have a zero shadow price, I mean this means that you are not going to give anything for an additional resource, then it means that you have that resource left. So why would you give any value to an additional resource if you are not using the ones you already have? All right, that was the story about shadow prices, which I would call marginal prices, and they were related to the changes in constraints. And in the next video lectures we look at the reduced costs that are related to changes in the objective function. See you there.